All right, welcome to this review. I'm going to review a little bit of speed, velocity, and acceleration for you. I think it would be a helpful video just for review purposes, so feel free to watch it at any time and pause and rewind as needed. Let's jump right into it. So speed and velocity, these two things are very closely related. Speed's the magnitude, right? How fast are you going? And our formula for it is speed is equal to distance over time. If we want to turn that speed and make it into a velocity, we just need to add a direction to it. And so the direction we could add could be like a compass. We could say east or north or south or west. Any of those would be fine. Or we could add something simpler like left or up or down. And either of those directions would create a velocity. And so in a coordinate system, a lot of times the velocities, if they're positive, are going to be to the right or up, right? So if we're throwing a ball up in the air and it's traveling upwards, we would give it a positive velocity. That would tell the person reading it that it was going up. If it's going to the left or if it's going down, for example, if we were to drop something off a building, like we're dropping a bowling ball off a building, that would be a negative velocity, be going downwards towards the earth. There's an important distinction here between average and instantaneous velocity. Average is going to be that total time. And so the formula for average velocity, we could write it like this. VF is equal to the final distance minus the initial distance. And we do the same thing for time. So what was the final time? Minus the initial time. And so that's going to find the average over the entire course of that time we were measuring the speed. The instantaneous would be at that given moment. And so if we're like driving a car from point A to point B, this would be what your speedometer on your car is reading. Or if you have a speedometer on your bike, the speedometer is going to give you that instantaneous speed. How fast are you going at that instant? Let's watch a race here and make sure I'm going to the right spot. So this is Usain Bolt's record-setting run, and we're going to use some of the data from this for some calculations. So I hope you enjoyed the German commentary there. If I move my picture, you can see that our time was about 9.58 seconds. So this is an incredibly fast human being, and we can use it to calculate exactly how quick Usain Bolt was going. So our distance divided by our time is the speed. And if we wanted to find the average speed for Usain Bolt for this record-setting run, we would take our total distance, which is 100 meters, and we would divide it by 9.58 seconds. And I forgot some decimal places here. Each of these should have a decimal place after them. They'll be important for our significant figures coming up. And so this is 100 with a decimal place meters. And so if we're going to type this into a calculator, we can go ahead and divide. And so when we do so, we get 10.0 divided by 9.58 seconds gives me 100.0 divided by 9.58 seconds gives me an average speed of 10.4 using correct sig figs meters per second. A lot of times it's difficult to wrap our head around what a meter per second really is. And so 1 meter per second, this is just kind of to help you remember stuff, not necessarily a conversion to use for dimensional analysis, is about 2.2 miles per hour. And so if Usain Bolt's going 10.4 meters per second, this is going to be about 22 miles per hour average speed. Now we can look at an instantaneous speed and we're going to see a different picture. So let's look at one of these sections. And I think this first section will be pretty telling here. So the very start of the race, typically you're going to be going a little slower here because you have to get up to speed from 0. So let's try it in our speed equation. So V is equal to distance final minus distance initial divided by time final minus time initial. And so if we plug all this stuff in, my final distance here would be the 20 meter mark. So we're just looking at this one section of the race. So 20 meters minus 0 meters divided by our times. My final time was 2.89. I missed the decimal place. 2.89 seconds minus 0 seconds. And so this is going to help us to figure out the speed at this point. So his instantaneous speed at the beginning of the race is going to be 20 divided by 2.89 seconds. And we get an average speed here of 6.92. So it's significantly slower than the 10.4 that he averaged throughout the course of the race. And so this is an example of an instantaneous speed at the given minute, or at that given instant. He was going 6.92 meters per second. We can graph speed using distance time graphs. And so whenever we're doing these graphs, time is always going to be on the x-axis. It is the independent variable here. The distance traveled depends on how long we've been traveling for. The distance will go on the y-axis always. And so this is a couple different lines here from different sets of data. The first line, letter A, is a pretty shallow line. Our slope is not very steep. And so we would say this is a little bit slower speed. And actually, the slope on the distance versus time graph is equal to the speed over that section of time. And so our slope here for line A, we've got a point right about here, which would be 1, 2, and we've got a point right here, which looks like 2, 1, 2, 3, 4. And so we're going to use our rise divided by the run to calculate what the slope is and what the speed would be at this given point. And so the rise over the run, we go up 1 and over 2. So my rise is 1, my run is 2. My units are given to me. I've got meters for my y units and seconds for the x units. And so I get an average speed, or a speed for this one, of 0.5 meters per second. Some other things to be aware of on a distance versus time graph. If you have a flat line, like if we had a fifth line here, line E, that just followed this 4 horizontally, this would be an object at rest, something that's not moving. It's just sitting there. Its distance position is not changing at all over time. It's just at rest, sitting there. You could end up seeing something like this. And so this graph would kind of be like the course of a runner or something as they're going along, and you get a changing speed over time, right? So initially we're starting here at the home base, and this person is leaving it and going 60 meters away. And so as they do that, they take a certain amount of time. It takes them 10 seconds to go 60 meters. So this whole section from time 0 to time 10, they have an average speed of 6 meters per second. That's 60 meters divided by 10 seconds. At that 10-second mark, and then for the next 5 seconds, the slope of this line is 0. It's a perfectly horizontal line, and so they start moving at 0 meters per second. They're taking a rest here. After they take their rest, we end up with this big long section where they go back to home, and then they go another 40 meters beyond it. And so this is going to give us a negative velocity. We cannot have a negative speed. So again, we'd calculate the slope of this line. It looks like we are going a rise and a run. We're rising by 20 and running by 5. So 20 divided by 5 would give me 4 meters per second for the speed here, and we're going in the opposite direction, right? So this would be back towards the house, and so on and so forth. So this is something you may see, and you might have to break it up into these sections. Another common question to ask is, how fast is the person going at time equals 30 seconds? So you'd have to look at this point, determine what the slope is of that section of the line, and then determine your speed. Acceleration. So the next thing after speed and velocity is acceleration. This is a change in speed or direction. So we could have either something that's speeding up or slowing down to cause an acceleration. Also, if speed stays the same and you're turning, like if you've got your car on cruise control and you just turn with the highway, that is also an acceleration because the direction is changing. That makes a change in our velocity. And so for acceleration, we've got a formula again for this. This is going to be acceleration equals the change in speed divided by the change in time. And we could write this out as VF minus VI divided by sorry about that, TF minus TI. So the final velocity minus the initial velocity divided by the final time minus the initial time. This should be an I. A lot of these types of problems for acceleration, you're going to see something being dropped. So we've got this person, let's say they're going to throw a bowling ball off the cliff. They're just going to drop it right off the edge. Acceleration due to gravity is 9.8 meters per second squared. And so what that means is that for the first second that this bowling ball falls, at the end of that second, it'll be going 9.8 meters per second as its speed, right? Initially, before we let go, of course, it'll be 0 meters per second. After another second passes, so at the second that it's been falling, that speed will increase to 18.6 meters per second. And if we let it fall again, we'd be looking at 30-some seconds or 30-some meters per second. So it's getting faster as it falls. And that's what acceleration means, that we're changing speed as we go down. So we wanted to calculate how fast is the bowling ball going at, let's say 3 seconds, since we can't see it in the picture here. We could plug it into our equation up here. So we want to know how fast is it going at 3 seconds. We know acceleration due to gravity is 9.8 meters per second. And we know some information about the speeds. The VF we do not know. That's what we're solving for. How fast is it going after 3 seconds? The VI, the initial speed, we do know. Here's my initial speed. It's not moving at all before I let go. And so that's 0 meters per second. Along the bottom here in the denominator, I've got my times. And so we said we wanted to know at 3 seconds, how fast is it going? My initial time, TI, is also going to be 0 because we haven't let go of the ball here at the beginning. So we're just going to plug a 0 in there. And we're solving for VF. The nice thing is these are both zeros, so we don't really have to worry about them in our formula. And so we get 9.8 meters per second squared, there should be a squared here, equals VF over 3 seconds. I want VF by itself, so we'll multiply each side by 3. And we get our VF to be equal to, plugging into my calculator now, 29.4 meters per second. And so this is only after 3 seconds of falling. Remember the conversion I told you to convert that into miles per hour is to multiply by 2.2. If we do that, that's 64 miles per hour after only 3 seconds. So you're falling really quickly at this point. There's one more type of acceleration problem I'd like to show you. Let's think we're talking about a car in this case, and I'll make an excellent car drawing here. If you have a car, let's say it's a real fast car that can do 0 to 60 miles per hour in, let's say, 3 seconds flat, how fast the acceleration does this car produce? And again, we're going to use the same formula. So acceleration equals the final velocity, which is going to be our 60 miles per hour. and we're going to subtract from that the initial, which was 0 miles per hour, and I need my per hour here. And we're going to divide it by the time, so that it would take 3 seconds to do it, and our initial time again would be 0 seconds. So these are going to cancel out again nicely. And now we're solving for acceleration, so how fast are we accelerating here? 60 divided by 3 is going to give me 20 meters per second squared as that acceleration of the car. One last part to this, all right, and I promise this is the last piece, is a speed versus time graph. So it's different than position time. Now we've got speed on the y-axis. Time stays on the x. These ones are going to show some acceleration. And so if we look at the first graph, graph letter A here, this flat line means that our object is not changing speed, right? Speed is staying at 10. So this is a constant speed. It's not stopped. It is moving, but it's moving at a constant speed. If we have a graph that's got a positive slope, like this one has a positive slope, the slope of that line, and remember slope is rise divided by run. If we have a positive slope like this, that means that we are accelerating. This graph here would show you an example of something that accelerates up until it gets to 8 meters per second, and then it holds at a constant speed at 8 meters per second. Again, you may see a section of a graph that looks something like this, and you might want to find the acceleration at any given ones of these points. Notice that we have a negative slope like we have between B and C. That's a deceleration. It's slowing down here. And that's all I've got for you. I know it's a little bit long of a video, but you're welcome to skip around, fast forward, jump ahead, and stuff like that. Hopefully it was helpful. If not, let me know how I can improve it in class, and I'll keep putting these out as long as people like watching them. Have a good one.